Alexei Latyntsev from Oxford. The title is Quantum Vertex Algebras and Cohomological Full Algebras. So please.
Oh, thank you very much, Jan. And yeah, thank you for the invitation. And yeah, hello, everyone. Yes, so today I'm going to be talking about some work I've been doing involving sort of factorizable or like vertex algebra analogues of quantum groups. So there are a couple of projects, and like both of which are going to be like part of my thesis. And then, so once I've talked about these results, I'll at the end talk more about like some questions and ongoing work. Okay, so to begin with, I'm going to introduce like the main concepts, sort of quantum group, cohomological algebra, vertex algebra, these sort of things. So all of these background concepts in the talk originally come from physics, and even defining them mathematically were sort of like tremendous like mathematical achievements. They're all related to each other. They sort of give links between other really interesting aspects of mathematics. And for instance, like in geometric representation theory and numerative invariance. But they're also quite difficult objects, and they're definitely not anywhere close to being fully understood. So for instance, take cohomological algebras. So they were defined in 2010 by Kuntsevich and Soyman after an immense amount of work by a lot of people and also a lot of false starts. And so the definition is meant to formalize the physics notion of an algebra of BPS states. So I'll quickly review like the definition of quantum homological algebras and then maybe talk a bit about the physics motivation. So let A be an abelian category. So for instance, coherent sheaves on a scheme representations of a quiver. So a first attempt to get an algebra structure from this is by Hall, which is where the name comes from. So the set of objects in A is sort of almost an algebra under this multiplication law. So given two objects in the category, if you have an extension, then the product of these two objects is just the extension. Okay, obviously not well defined. There's more than one extension. So perhaps we should just take the sum of all extensions. This almost works, but because of like, this is just like not really canonical in any way. So you have to put some weights in here, sort of measuring like the Hom spaces between these objects. But if you do this, then this gives you an algebra structure on the set of isomorphism classes of objects in this abelian category A. And the condition is the category needs to be hereditary. So approximately the higher Hom groups have to be like finite sets. Okay, so this is sort of a first attempt at getting some sort of algebra structure out of an abelian category and extensions. So the second attempt, and the thing which actually sort of generalizes, well, it mathematicizes the physics notion of algebra of BPS states, is that of a cohomological algebra. Okay, so how does it work? You replace the set of objects in this abelian category with the stack whose points are objects in this category A. The algebra structure comes from the correspondence. So there's a stack parameterizing short exact sequences in A. So a point in this is just a short exact sequence. And this admits two obvious maps, one to moduli stack times itself, which takes the two outer terms, and one just the moduli stack. Okay, now this no longer gives you an algebra structure on points of M, because for instance, the fiber of Q is not a singleton. So you should sort of expect to get a algebra on homology of M, or rather cohomology. So this is the definition of cohomological algebra in the simplest case. So if the dimension of this abelian category is less than or equal to 1, so this is homological dimension. So examples of this are coherent sheaves on a curve or representations of a quiver. Then the cohomology of this moduli stack, so this means L-adic cohomology, sort of Durand cohomology, basically any like any cohomology theory coming from a sheaf theory of the six functors. Yes, so, but for the future, I'll just say cohomology. So the cohomology of this moduli stack is an algebra under the product push-pull. Okay, so this is an algebra structure coming from extensions as before. So this is the coha that I'm going to be considering is going to be important to me. However, there are lots of variations. So for instance, if the dimension of the category is less than or equal to 2, so for instance, coherent sheaves on a surface, then it turns out not the cohomology, but the Brelmore homology is the correct thing to consider. So it turns out that this thing is an algebra under push-pull also. Right. Although historically this was not actually the first thing considered. So in the considered Soilman paper, they considered they approximately, so if you have a Clavier-3 category, like the cohomology of the moduli stack is not the correct thing to consider. You need to sort of consider the cohomology of the moduli stack with coefficients in a certain perverse sheaf of vanishing cycles. And then it turns out this is the correct thing to do. However, this story is sort of orthogonal to the story I'm going to tell today, so I'm going to brush it under the carpet for now. Okay, are there any questions?
Maybe not orthogonal, but it's a special case.
Yes. Yes. Okay, so I'll very briefly, so given the seminar is called the M seminar, I'll very briefly talk about sort of the physics motivation for all of this.
Yeah, but you don't know what M means. It has nothing to do with physics.
Oh, it's not M theory.
Yeah, many people think that way, but it's not. But anyway, go ahead.
Okay, sorry about that. Well, I'll say it anyway. So if you have any like n equals 2 supersymmetric field theory,
not any, probably 4-dimensional, otherwise you're in trouble.
So I was wondering
if it's 3D n equal 2, I don't think you will see any algebra of BPS states.
So what I've heard that in the one-dimensional case, when you have the cohomology of Riemannian manifold M, so the underlying Hilbert space of differential forms, and then the least superalgebra is this, so Laplacian exterior derivative and its adjoint, then maybe this is not the same notion of BPS state.
I don't think, hold on. Well, it depends on what do you call 1D n equal 2. Theory, I don't know, probably except of the Morse theory, you have nothing. I don't think you have, you just have one supercharge and the conjugate. So then I think it's roughly definition what is written.
Yes.
Yeah, okay.
Well, okay, this is perhaps more motivation then, rather than literally what. Well, okay, so yeah, so the algebra BPS states in this case, so it's the kernel of the Laplacian, which by Hodge's theory is just the cohomology of this manifold, and this has an algebra structure, which is part of the general pattern that you expect the algebra BPS states to have an algebra structure. And so, like, the more correct...
sorry, now I'm totally confused, because kernel of the Laplacian is a space of harmonic forms.
Yes.
There is no associative algebra structure on harmonic forms, only an infinity structure. So then I don't know, what do you mean by algebra structure?
Well, I mean, associated to any harmonic form, like you have a cohomology class.
Yeah, you do have, but you cannot multiply product of two harmonic forms. It's not a harmonic form. You should project, and so you get the infinity structure from the quasi-isomorphism of cohomology with the space of all differential forms. You basically transfer the product from omega m to HBPS. Then you have only a infinity structure.
I'm sorry about that then. Yeah, yeah, I stand corrected for that. Yes. Okay. And basically, so I believe the example, so the sort of example, the Clavier-3 category examples come from like the 10-dimensional string theory. So you have some sort of 10-dimensional theory, you compactify it along a Clavier-3 fold, and then, okay, what physicists will say is that you then consider D-branes, sort of even-dimensional D-branes in this 10-dimensional theory. And D-branes are sort of meant to correspond to elements in the derived category for coherent sheaves.
No, they don't have to be even dimensional. There are, so you look just for the boundary conditions for superstring. It's, I mean, you consider 2A type. Yeah, but it doesn't have to be 2A. Yeah, it's up to you. Yeah, okay.
Yes. Yes, and I think this is why you should consider, this is why you should expect this sort of thing. Why you might expect like an associative algebra structure coming from coherent sheaves. Okay, this is perhaps an olive branch to the physicists, and like apologies to any mistakes made, and I will return that.
Yeah, actually too many of them. So probably you should skip this physics part, because it's no, yeah, BPS, D-branes, it's
yeah.
mathematical seminar.
Okay, I will now talk about vertex algebras. So I'll very briefly motivate the definition of vertex algebra. Oh no, firstly I'm going to talk about like why one might care about cohomological algebras. So like very important objects. So if you take so a very important example of a dimension 2 abelian category is a pre-projective algebra of a quiver. And so Yang and Zhao showed that if you take its Borel-Moore homology, then this is very closely related to the so-called affine Yangian of the Kac-Moduli algebra attached to this quiver Q. Okay, so you actually have to do something called doubling, but it's very closely related to affine Yangian. So secondly, if A is a Klein-Bell3 category, then the dimensions of this coha are closely related to DT invariance. I should also say that like defining this coha structure for a GML Klein-Bell3 is very hard and sort of very interesting. And even in the case of like toric Klein-Bell3s, so for instance, like A3, there's some connection to W algebras. So like this coha is is approximately like a W vertex algebra. Something which is morally related is the construction of Gronowski of Nakajima of a vertex algebra structure on homology of the Hilbert space of a algebraic surface. So Gronowski showed that this thing is a Heisenberg vertex algebra, and then this structure essentially comes from correspondences. So correspondences between one Hilbert scheme and the other. Okay, and there is a sort of generalization to higher rank, which I won't talk about. Okay, so are there any questions about cohomological algebras? Okay, now I'll move on to vertex algebras, which with apologies to the experts in the audience, I will just sort of sketch a definition, which is sort of, I think, a bit faster.
Maybe,
right.
Alyosha, maybe to your previous page. There is also a series of works of Ben Davison, and so I think he explained clearly how not necessarily affine, like affine Yangian, so this Yang Zhao, it's some sort of dimensional reduction from three-dimensional story. So then, in fact, this part 2 by the work of Davison, it contains part 1, and well, without vertex algebra structure, blah blah blah. Yeah, well, in some sense, it contains everything which has smaller dimension, like surfaces and in fact curves. So it's kind of, there is some hierarchy. Okay, sorry. Yeah.
Oh no, thank you very much for that. Okay, so now I'm going to
actually, sorry to at this page, when you said the high rank Schifferman Vasarov in the high rank, in what sense? Is the Gronowski and the Nakajima, was that in rank 1 or?
Yeah.
So basically that was a GL1, right?
Yes, yeah. So that's the GL1 case.
Okay.
Because like the W algebra for GL1 is just the Heisenberg algebra.
Okay. Yeah. Thank you.
Yep. Okay. So yes, thank you very much for that. I'm now going to talk about vertex algebras. So I will. So instead of saying actual definition, I will sort of sketch the definition, then give examples, which is sort of most important. So okay, toy model. Okay, so okay, so physicists will, when introducing vertex algebras, will sort of like draw particles going in, interacting, then going out. So when you do this sort of in string theory. So instead of particles moving in, interacting, then going out, you have sort of like S1s doing the same, and they sort of trace out a Riemann surface. And the structure of a vertex algebra is trying to capture a vertex algebra is a vector space, and this vector space is approximately the state of Fourier modes of sort of asymptotic string states. And the extra structure, the extra structure on this vector space is what happens sort of when you sort of collide these strings. Okay, so how mathematically are you actually going to formalize this thing? So you take a formal neighborhood, and the structure of on a vertex algebra is a so-called field map. So for any state alpha in this vector space V, you have a map from V to V Laurent series Z, which sort of measures the effect, like adding a particle alpha at a point Z to another particle taken to point 0. Yes. Yeah. So this measures that effect. And so the axioms of vertex algebra are actually quite simple. There's a commutativity relation between these two fields, which approximately says sort of if you add a particle at Z and add a particle at W, then this approximately commutes if you do it the other way around. Okay, so for what will follow, the definition does not actually matter because we'll be working with explicit examples of vertex algebras, and I will just sort of give you some examples now. So the thing which realizes the toy model is the jet space of a scheme X. So the jet space of a scheme X is a space of maps from the formal disk into X. So this is an in scheme, and it carries a vector field, sort of given by loop rotation. Right, so in particular, its space of functions is a commutative algebra with a derivation. Okay, and therefore this is a vertex algebra where the field of an element alpha in the function on the jet space is given by, you multiply by alpha, then you apply e to the power of this vector field Z. Okay, and then this is the thing which, okay, so if you were made uncomfortable by the stuff I was talking about in the last slide, this is what you should think of it as actually being. Okay, so these things are called holomorphic vertex algebras, and they're equivalent to the categories of commutative algebras equipped with a derivation. So in particular, if you take the derivation to be 0, you get that any commutative algebra is in particular a vertex algebra. And you should think of this as like that these strings sort of like not interacting, or the interaction not depending on the point Z on this Riemann surface. Okay, whatever. So the most important example of a vertex algebra, which is sort of not a holomorphic vertex algebra, is the so-called Heisenberg vertex algebra. So it is as a vector space, it has a grading, and its associated graded is simply functions on the jet space of A1. So it's a Fock space on negative modes, on like B-1, B-2, and so on. So just as there's a generators and relation as definitions for algebras, there's also a generators and relations definitions for vertex algebras. So we have this vector space, and to define a vertex algebra structure on it, it is enough to say that it is generated by a single field, which will be of Z, which is the field of this element B of -1, subject to these OP relations. Okay, so this is an element if you apply an element of this vector space to both sides, this gives you an element in sort of V sort of formal power series in Z inverse and W inverse. Okay, so this actually uniquely defines a vertex algebra structure on this vector space. But maybe equivalently, it is better to be a little more explicit. So this OP is actually equivalent to the modes of this. So the Fourier coefficients of this field acting as a Heisenberg algebra on this vector space V. So you could equivalently define the Heisenberg algebra to be you take the loop space of the one-dimensional Lie algebra, you essentially extend it, and then you take a Verma module of this Lie algebra. Okay, and then it turns out that this thing has this is an equivalent definition of the Heisenberg algebra. Okay, so are there any questions?
In this Heisenberg, the P sub n with n positive or 0, which does not appear when you...
So the Bn with n positive acts locally nilpotently. Is that, sorry, was that your question?
Yeah, well, from the H hat, that's obvious, but from the the polynomial ring from the grid V, so that the notation definitely confuses me. That part only gives to all the exponents of.
Are you asking about this equality? So this is an equality as commutative algebras with derivation.
That's right, but you have those notations B sub -1, -2. Right?
I see. Yes. Yes, I agree. I agree. These B -1, B -2 are not formally the same as it's not the same.
That's
as
right.
Yes. Yes. Are there any more questions? All right. In that case, I will continue. So there's 3 important examples of the Heisenberg, and the last one is the lattice vertex algebra is the one which is going to be most important to this moduli spaces story. So firstly, there's the affine vertex algebra, where sort of the ambient space where the strings are moving is approximately the dual of a finite dimensional Lie algebra. So as for the Heisenberg algebra, it's got a generated in relations definition, where it's generated by fields, a field for each element in the Lie algebra, subject to a similar relations. So here, kappa is the killing form on the Lie algebra, and this is just the bracket in the Lie algebra. So secondly, they're affine W algebras, whose associated grades tend to be jet spaces of coadjoint orbits, and it's so it's a one-parameter deformation of a certain algebra, and this algebra is you take a nilpotent element in the dual of the algebra. Okay, it's killing dual to a nilpotent element, and then you take the action of the loop space Ln plus on the dual of the associated affine Lie algebra. Okay, so this action is Hamiltonian for certain. So this action is Hamiltonian, and you take the Hamiltonian reduction, and then functions on this thing as an algebra, and then W algebras are sort of a quantum version of this. So you can essentially run this Hamiltonian reduction procedure. You can sort of quantize it, and that's approximately what W algebra is. Okay, so these are sort of 2 of the most culturally important generalizations of Heisenberg. And the third one is lattice vertex algebra. So I will not say precisely the fields in the lattice vertex algebra, but I will motivate sort of why you might expect
can you say the moment map mu is from where to the G star?
Sorry?
The moment map mu from where to G star? Where's the symplectic?
So this is the group, and this is the thing it's acting on.
Yeah, so that is the symplectic manifold, right?
Yes.
And the mu is from the. Okay.
Yeah. Yeah, so it's from. So this is a bit confusing. Is the Lie algebra? So it's from here to the Lie algebra.
Yeah, no, that the dual is a symplectic manifold.
Yes. Yeah, that's right. So so lattice vertex algebra is a bit like the Heisenberg vertex algebra, but you sort of the underlying space you're sort of considering is the torus. And so as a vector space, it's simply you take the Heisenberg vertex algebra, sort of take the n-fold tensor product of it, which is itself a vertex algebra, and then you tensor with the group algebra of the lattice lambda. Okay, why are you doing this? You should maybe think about this as being the fact that there's sort of lambda many homotopy classes of S1s inside the torus, and the universal cover of the torus is AN, which is why you might expect a vertex algebra structure on this. Okay. Yes, and you can write down like formally what the fields are, but it won't be so important. Okay. So Right. Now we get to sort of more modern stuff. So more recently, Joyce has found like a huge new class of vertex algebras. So he sort of found them whilst researching about DT invariants. And they tend to sort of be lattice vertex algebra flavored. And I will now explain what they are. So if you have an abelian or triangulated category A, then the homology of its moduli stack of objects is a commutative algebra by the direct sum map. So the direct sum map on the category gives you a direct sum map on the moduli stack, which gives you a commutative algebra structure on the homology. Okay. So if the category is k-linear, then the action of k star on objects gives you, on the level of geometry, an action of the group stack BGM on the moduli stack. Okay, so what is the homology of this thing? It is a polynomial algebra generated in one element in degree 2. And if you push forward by this element, so if you sort of act by this element, then it gives you a derivation of degree 2. So then the homology becomes a differential algebra.
And here, the homology is just the ordinary, or the Borel-Moore homology.
No, so when I say homology, I definitely mean homology, because when
not a Borel-Moore, right?
No, yeah. So it would be wonderful if you could get this to work for Borel-Moore, but so far it's not being able to. Like there's some, like I think it's like Borel-Moore. This map is absolutely awful. It's not proper. It's just horrendous, and so you should not expect to push forward by Borel-Moore via it.
Yeah, I was wondering that earlier you using the push forward functor.
Yes. So yeah, so
that makes sense.
Yeah, so earlier you could push forward by the short exact sequence map P, because P is quasi-smooth if the category is dimensionless and equal to 1.
So Alexei, I'm a bit confused. You say A is any linear, k-linear category, blah, 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 without any algebra geometric structure. What do you mean by homology of the stack? You do not have any stack structure unless you impose additional restrictions in your category.
Yes, so secretly, so secretly the actual definition is not in terms of A, but in terms of this stack MA, which is called X, and these axioms you just turn into axioms of the space. So the axioms of the space are, so it's a commutative monoid in the category of stacks. So you get a direct sum map. This commutative monoid object has an action of the group object BGM, and it also has a perfect complex, which we're coming to now, on this moduli stack times itself, which has a bunch of properties, which I will not get into these properties now. So essentially, it needs to be compatible with this direct sum map and this action map.
But MA is some kind of a space. It belongs to some class of,
yes,
at least DG, maybe infinite stacks. I don't know. It depends on your taste. And with some additional structures, these bullets. But
yes,
the difficult part is actually to state what this MA is, because probably you will need some functoriality or some sheaf theory. Who kind of, I'm ignorant, who wrote that kind of background foundation?
Maybe?
I mean, if you have just a triangulated category, you do not have a good stack of objects. So what kind of triangulated category or even a abelian category do you consider? I mean, because you will apply it to stacks of objects of some categories. So you have to be sure that these stacks belong to the class which is good for you.
Yes, so I don't. Okay, so because in day-to-day life, I'm only actually caring about like particular examples. So I don't know the answer to this, but I think the place to look for the answer is, I think Tone has written about this. Maybe this is a.
All right, so maybe indeed let's postpone it. It's something in foundations. Okay.
Yeah. Yeah, so secretly, so I'm saying this is on the level of categories, but secretly this is actually a statement about spaces and its structure, but it's a bit simpler to state it in terms of moduli, because all examples will just be the moduli stack of objects in the abelian category or triangulation category. Okay, so having this differential algebra structure makes this into a sort of holomorphic vertex algebra structure. So a vertex algebra where these interaction terms have no poles. Okay, so if you know the notion of Borchards' bicharacter twist of a vertex algebra, the following is an example of this. So attached to any perfect complex satisfying a list of axioms, the following map gives you a vertex algebra structure. Okay, so it turns out that it's actually a lot cleaner to write it in terms of the dual vertex co-algebra structure. So what is that? So it takes an element alpha in the dual, so in the cohomology of this moduli stack, so it pulls back by this direct sum map. So this gives you the first vertex algebra structure, the dumb one. Then it pulls back by this action. So you're identifying here the cohomology of BGM with polynomial algebra in Z. Okay, so this would give you the holomorphic vertex algebra structure. And then you dot with the pullback of the Euler class of theta. Now, unless theta is a vector bundle, the Euler class of theta is not actually defined. So this thing is a definition rather than inequality. So by the splitting principle, if theta is a vector bundle, you have this equality, and then in general, you just make this definition. Okay. And then the theorem of Joyce is that, so if you take theta to be, so this is the x complex on the moduli stack, whose fiber above a pair of objects AB is just x of AB. This is the swap map, and this is dual. So the fiber above AB is just x of BA dual. Okay, and then Joyce's main result is essentially this thing gives you the structure of a vertex algebra. All right, and then your questions? Right. So I'll make a quick few questions and remarks about this construction. So firstly, if you take the derived category of representations of the quiver, you get a lattice vertex algebra on the lattice given by K0 of representations of the quiver. Okay, and then similarly for coherent sheaves on curves and surfaces by a result of Gross. Yeah, so you get a super lattice vertex algebra in that case. It's not known whether you can factorize this definition, so whether there's a factorization algebra rather than just a vertex algebra. And it might be an interesting task to see if this is true. Also, it's not quite clear. I might talk a bit about this at the end. It's not quite clear what the relation to Grodnowski-Nakajima construction is, despite it looking, on the face of it, somewhat similar.
Could you please remind, do you mean Grodnowski-Nakajima only for Hilbert schemes, rank 1 instantons, or
only Hilbert schemes?
Only Hilbert schemes.
I mean, I've not really thought about the instanton case because it seems to be, one should think.
What I mean that it's kind of better to understand, I don't know better or not, but you can understand this Hilbert scheme story as a special case of this W algebra, yeah, which includes instantons of higher rank rather than one. And then it's quite clear that you deal not with lattice algebras, but with more general structure, which actually kind of reconsidered with Rabchak, Young, and Zhao, and then with Diaconescu and others, that basically it's at least two-dimensional. And you have somehow to remember the potential, which Dominique certainly doesn't see. Because what he does, he just symmetrizes X, and this is it. So sort of an attempt to make it two-dimensional, but the potential is missing. So this theta seems to be not sufficient to connect it to, at least for me, to Nakajima and other and higher rank stories. So then,
yes, I think this is. Yeah, I agree. Like this thing is like, it's the thing I'm least sure about whether it would work. It's also worth remarking that, as you said in the critical, like when you're taking cohomology with respect to a perverse sheaf, it's sort of unclear how to relate this to Dominic's construction, and similarly for Borel-Moore homology.
So I'm curious at this point, why Dominic, who certainly knows about this sheaf of vanishing cycles, did he try to add it to the story? It's certainly relevant as
Yeah, I think so, but I think it's just I think it's the compatibility with the addition map. That if you try to just do it naively, it fails.
Yeah, probably not naively. Because as of now, there are examples when indeed you can do that. And it's related to Grainovsky and Nakajima. So that's what I mean. That probably you should try, or he should try harder. Okay, thank you.
All right, thanks very much. And then there's also this idea floating around that passing from the abelian category A to its derived category should have something to do with doubling. So I might talk a bit about this at the end, but I'll skip over it for now. Right. Well, the question which is most relevant for this talk is that taking theta equal to the symmetrized X complex is not actually the most natural thing to do when it comes to cohas. So symmetrizing it's interesting and might have something to do with doubling, but taking theta equal to the X complex is really what you want to do. So if A is even clavial, this thing also gives you a vertex algebra structure. But for a general abelian category A, the resulting structure is, so it's not quite a vertex algebra. So it turns out that so the main axiom that I glossed over and didn't give you of a vertex algebra is weak commutativity. So these fields have to like approximately commute. And so if you take theta to be the X complex, then in examples, what you'll get is sort of a weakly associative vertex algebra rather than a weakly commutative one. So it's like, okay. So it turns out this is actually a good thing because sort of quantum vertex algebras and quantum groups are sort of, in a sense, like even more interesting objects than sort of vertex algebras and algebras. Okay, so before talking about this story, I'll briefly like sketch the story of quantum groups. Right. So quantum groups came about in the 80s as like an answer to the question about like what definitions of U of G are. So for a long time, this was sort of considered a dead subject because if G is a sort of finite dimensional symbol in the algebra, it's got no definitions as an algebra. Well, then Drinfeld came along and said that it's better to view this thing not as an algebra, but to remember the coproduct structure on this thing. So you view it as a bialgebra, and then maybe you need a bit of extra structure. So this thing called an R matrix, which measures the failure of commutativity. So I'll state the definition for a quantum group in a second, but something which will be relevant is so this is essentially the moral definition of a quasi-triangular bialgebra. Is that if A is a quantum group, the quasi-triangular bialgebra, then its category of representations is a braided monoidal category. Okay. So one of the things Drinfeld did when introducing these objects is show that U of G it admits a one parameter deformation UH bar of G, and this deformation is approximately unique. And so I don't have the time to go into this now, but you can identify the category of representations of this deformation with a certain geometric category of D modules on Laffman-Grassmannian. Okay. So these are what quantum groups are. So the definition of a quantum group is, well, okay, so this is the definition. This is the definition of a bialgebra, and so a quantum group is a bialgebra, so an algebra with a coproduct, such that the coproduct and product are compatible. So they're compatible in the obvious way, but I've written out this diagram out in full because I'm going to write out the analog in vertex algebra land in a second. And it's got an invertible element R in A tensor squared, satisfying the Yang-Baxter equation and some other compatibilities. So the important part is this diagram essentially. So okay. So the main point is now of a quantum vertex algebra. So let's see. So a quantum vertex algebra is a compatible algebra and a vertex coalgebra structure. So And this vertex coalgebra structure might not be weakly co-commutative, but it's weakly co-associative, okay, which are compatible in the way which is exactly analogous to the definition of a quantum group or quasitriangular bialgebra. And moreover, you want a so-called R matrix, which is now an endomorph, a map from V tensor V to V tensor V double bracket Z, satisfying analogous axioms to the quantum group story. So here they are. So these axioms are actually in examples quite easy to verify. So I'm not really going to focus on them. It's this thing which is the important thing: the compatibility between the cohomological structure and the vertex algebra structure. Okay.
You tell me what the sigma here is just a switching the two factors, or?
Yeah, sorry, yes. So thank you for that. I didn't state it. Yeah, sigma here is just switching the two factors.
Okay, thank you.
Yes, and that also appeared in the definition of bialgebra. Okay, so a very natural question is, okay, so a quantum group is sort of morally an object whose category of modules is rated in an Euler category. And then a very natural question is sort of like what does the structure of representations of this object have? Okay, and it's a question that I don't know the answer to, and sort of interested in thinking about. Okay, so are there any questions about this? All right. In that case, I will go to the main theorem. So let A and a abelian category be coherent sheaves on a curve or representations of a quiver. Okay, so it's a dimension 1 category. So the cohomological algebra structure is defined, and it's an abelian category. So a vertex coalgebra structure, which is non-weakly co-commutative, is defined on the cohomology of the moduli stack. Okay, and then the theorem is that these two structures are compatible. So the cohomology of the moduli stack is a quantum vertex algebra. Okay, so one thing to note is that this is a many results relating cohas and vertex algebras sort of relate cohas to like the algebra of modes on a vertex algebra, and this is not of that form. So it's a genuine relation between like an algebra and a vertex algebra. And I should also say that like most notions of like deformed vertex algebra are sort of like quite poorly understood. So like most open questions about quantum vertex algebras, like graded vertex algebras and so on, are not well understood. And there are like many sort of like competing definitions. So this might be viewed as like partial evidence that this definition might be like the correct one, or at least in certain contexts. Okay. So as I said before, the non-trivial part of showing this thing is a quantum vertex algebra is sort of showing the compatibility between the cohomological product and the vertex coalgebra structure. Like showing this thing satisfies the Yang-Baxter equation. Well, okay, I'll define what RMZ in a second, but when you've defined it, showing it satisfies all the compatibilities is actually quite easy. So I'll just gloss over that. So this is the main thing. Why is the cohomological structure and the vertex algebra structure compatible? Well, this is the reason essentially. Remember that the vertex coalgebra structure was defined using the Euler class. So you sort of pull back by the direct sum map, you pull back by the action map, and then you dot with the pullback of the Euler class. Okay, so this is the vertex coalgebra structure. So if you want to have any hope of making this commute, you need to make the coha defined in terms of the Euler class of theta 2. Now, the basic reason this is true, why there might be some relation between coha and theta, is that if you take this diagram, so short exact sequences mapping to moduli stack, moduli stack squared, then the tangent complex of this map is equal to theta, or rather the pullback of theta via q. Okay. So with all of this set up, yes, you set this R matrix equal to, so this is the factor this is the correction factor in the vertex coalgebra structure, and this is the correction factor for the sort of symmetrized theta. So this thing is 1 if theta is symmetric. So for instance, if A is 2 Clavial, or so for instance, if the quiver is symmetric, this thing is just 1. Okay, and this is and then the vertex algebra is actually this vertex algebra is actually a vertex algebra rather than a non-commutative vertex algebra. All right. Are there any questions? All right. So I'll now talk about how you might a sketch of like how you might actually prove this. So we're doing time. Okay. So the basic idea is that you consider the split locus. So the locus of objects in this abelian category, which is sums of two objects. Okay, so this map gives you an injectional cohomology when you pull back. So instead of considering push-pull, you might as well consider, instead of considering pull-push, you might as well consider pull-push-pull. And this is sort of the same data. Okay, so when you see a diagram like this, the natural thing to do is obviously to take the pullback. And this pullback parameterizes a short exact sequence with a splitting of the middle term. A short exact sequence, the splitting of the middle term. So note that the middle term splitting, so if you have if you can express E as a direct sum, this does not mean that the whole short exact sequence splits as a sum of two short exact sequences. Indeed, there's a map of GM on this moduli stack by sort of acting by weight 1 on this bit and weight minus 1 on this bit. And this point is fixed if and only if it splits up as like a sum of two short exact sequences, like this. Okay, and yes. So now, if you want to, so you have a fixed point of a torus action, and then so the thing to do is consider abelian localization. So if you want to compute pull push pull, this thing is a pullback square, so this is the same as pull pull push. And now you apply abelian localization, which says that if you push by I and then pull back, this is the same thing as dotting with the Euler class of the normal complex to I, which you can show by computation is something like the Euler class of theta. There's some relation between.
Now I'm totally confused. M is a stack or what?
Yes.
So I'm afraid I heard that there is this abelian localization, at least Adil Khan told me that he had, but it's not in textbooks. I don't know what is a localization for tori acting on stacks, on Artin stacks. So what is it? Do you assume that we know and agree?
So basically, like what you need to do is that you need so what the result that you need is a certain well, so there's like two separate problems here. So firstly, it's that this thing is singular, and secondly, is that this thing is a stack. So I'll talk about the singular phenomenon in a second. But so as for the stacky phenomenon, basically, like everything works as before, but you need to show that like certain cohomological classes are torsion.
So it's sort of a nice statement, but I wish I understood what does it mean. Okay, let's consider sort of a quotient stack, like quotient of, say, I don't know, algebraic variety by an action of a group, let it be GLN. All right, and in addition, you have an action of the torus in this quotient stack. So I kind of do not understand how these two things interact. Of course, if the action of the torus is free outside of the fixed points and maybe in a stacky sense, then at least I can imagine that, but if it's not, so I'm kind of, I do not have intuition, especially if you have DG stacks, which you probably do. So what?
I think DG is not an issue here because cohomology sort of only sees the classical part.
Yeah, I mean, yeah, probably, but okay, but anyway, what do you do? Basically, I mean, a kind of a little bit primitive version of that is Belianitsky-Berula story. So if you have an action of the torus, yeah, on an algebraic variety, so you have kind of a cell type decomposition, like algebraic Morse theory, that you decompose your variety into the union of, roughly speaking, something like normal bundles to the fixed point sets. Now, so is it true for Artin stacks? So you still have similar type of results, so I'm kind of confused.
I don't know. I don't believe it's true in full generality for Artin stacks.
But you say something about abelian localization. Is there a reference so we can read?
So I think so I do write something. I do write something about this in my paper. There's also a paper
Okay.
I'm writing about with Adil Khan and
okay,
which is I think coming out soon, which might have a good exposition of this.
all right. So as for published, it's your big paper, last year big paper. Okay. Also, yeah, I invited Adil Khan. He probably will give a lecture series on that. Okay, great. So it's not something which was known to Atia and Bot. It's very, very recent. Essentially, it's not published except of your thesis, your paper. Okay, great.
Right.
All right.
Yes. So I will. So I'm running out of time a little bit, so I will just be a bit speedy.
Could you explain a little bit about this SES2? Because I mean, the map
yes, of course. So this is a squared. Sorry, this is like that times itself. So this is just if you have a short exact sequence, and so the action of this thing is so GM sort of acts. Okay, so the actual action is that you replace. Imagine you've got. I'm not sure how to explain this quickly. So you for each element in GM, you have an endomorphism of automorphism of E, which acts by this on by weight 1 and this factor by weight 2. So in particular, you act on short exact sequences by sort of like.
Yeah, I try to understand how the I will get to a split short exact sequence.
So basically, like if you have two short exact sequences, you can take the direct sum, and then this gives
you
you
take the direct sum on both
middle.
ends, right?
Yeah.
Okay.
So yeah, but then you just forget the splitting of the two things on the side.
Okay. Well, thank you. Yeah.
Okay.
I was thinking of the short exact sequence with the 4 terms.
Oh no. Yeah. So it's not that. Yeah. Okay. So this is the idea, and so you relate the cohort product to push pull. Okay. All right. Right. So I'll briefly talk about how you tackle the problem about this thing being singular. This is a slightly different problem. So, okay. So this is what abelian localization is. It relates so this is the 1980s statement of it. So if you have a manifold with a torus action and Z is its fixed locus, then Atia and Bot proved that their equivalent cohomology is sort of isomorphic modular torsion. So, so some of the results in the paper, like replace this manifold with say a singular space. So firstly, it works not on the level of sort of like cochains and like singular cohomology, but it works in the language of like the 6 functors. So in particular, it's like you can get a statement for like L-adic, Durand, singular cohomology, and then if you work a bit more, you can also get statements for things which are definable using the 6 functors, like Roll-Moore homology, Chow. Yeah, it also works for general derived schemes in some Artin stacks. Okay, and the general like result, the headline for this is that if you localize, you sort of kill all singular behavior, and then these singular schemes behave, these singular spaces behave like smooth spaces, at least the equivalent cohomology after localizing. Okay, right, and the key object is the bivariant Euler class. Okay, so so approximately what the bivariant Euler class is this. So if you remember from your first course in algebraic topology, this is how you define the Euler class. So if E is a vector bundle over Z, then there's a long exact sequence on cohomologies. And you've got this map, which is multiplication by the Euler class. So it turns out you can sheafify this result to get a distinguished triangle of sheaves of say, vector spaces on a topological space. And this this distinguished triangle actually exists in, say, the derived category of L-adic sheaves on a stack. So this is like a very general result. And you can simply define the Euler class, the sort of the bivariant Euler class, to be an element of the bivariant homology of the map of this closed embedding, of any closed embedding from Z to X, and then dotting it, yeah. And so, yes, yeah. Right. So for any closed embedding, you have this distinguished triangle of sheaves. So this could be L-adic sheaves, homology modules, or something like that. It doesn't really matter what model of sheaves you use. Okay, and so if this closed embedding has a cosection, so if, for instance, it's like the zero section of a cone bundle or a perfect complex or something, so it sort of has a cosection, then this map is dotting by not an element of the cohomology, but an element of the bivariant homology. And its definition is essentially basically analogous to the usual definition of Euler class, but in bivariant homology. And what is bivariant homology? So it's a sort of analog of cohomology or homology, which was introduced by Fulton and Thurston, and they're sort of very good for studying singular spaces. Okay, so you can also define it in terms of six functors. And I will gloss over this now, but in the paper I showed that this notion of bivariant Euler class satisfies a lot of nice properties. So this is sort of justifying that this is the correct notion. So it's functorial with respect to pullbacks of the base. There's a Whitney sum formula for perfect complexes. So you need to work in localized equivalent cohomology for this. And there's a sort of abelian localization formula. Now, this abelian localization formula says that this bivariant Euler class, which is like an element of the bivariant homology, is just push-pull, which is the usual statement of a tier-bot abelian localization. Now, this is actually not very useful because this is not a genuine cohomology class, which is what you want. And what you need to do to get this to work is use a cohomological shadow of the exponential map. So in topology, the exponential map gives you a pullback map on bivariant homology groups. And it turns out that in algebraic geometry, this exponential map no longer exists, but this pullback map still exists, at least in the smooth case. So if you have an embedding of smooth schemes, you get this so-called specialization map, which is an isomorphism. Now, in the singular case, you no longer get this. So this map does not exist, but it does exist on the level of localized equivalent cohomology. So this is another example of the fact where localizing sort of kills singular behavior. And I showed that sort of this bivariant Euler class is compatible with this shadow of the exponential map and also fundamental classes. And then you can use this result. This is the punchline. You can use this result to compute CoHA diagrams. So if you have sort of CoHA diagram, X maps to Z and Y, and you have this X bar, which is sort of like the fixed point of a torus action, then you get that this CoHA map is related to the CoHA map on top, dividing by the Euler class. Okay. Right. And so this is exactly what happens in examples. So for instance, I will now have to breeze through the slides quite quickly. In Considerich and Soyberman's paper, they give a formula for the CoHA in terms of shuffle products, and you have this 1 over Euler class type term. And it turns out that you can write down this thing, and this is actually 1 over the Euler class of this map. So this is an example of that phenomenon. Secondly, if you apply this result to coherent sheaves on curves, you can get I got like a partial new result for formulas of CoHAs. So it's expressing the CoHA product for the moduli stack of coherent sheaves on the curve in terms of 3 simpler CoHA products. So the rank 0, 0, 0, 1, and 1, 0. So extensions of a rank 0 by rank 0 coherent sheaf 0, 1, 1, 0. And you can, to various degrees, you can understand these maps quite well. Okay, and then this method might be able to work for other cohas, for instance, Brell-Moore and perverse sheaf critical cohas. Okay, and very briefly, I'm also, there's no time to really speak about this, but I'm also thinking about how you might be able to get quantum groups to arise out of the Joule algebras of Q-deformed vertex algebras. But I think that's a story for another time. Right. So
yeah, I understand that you kind of you force yourself to finish on time, but you don't have to. I mean, if you want to say a few words about the slides which you just kind of browse and just go ahead. So
I might talk about which one should I talk about? Okay, perhaps I will just, but perhaps it makes more sense to Okay, I'll talk a bit more about this then. So
that's great.
Sorry?
That's great. I really want to know that.
That's good. So this is a work in progress project. So
and also the first part, there should be the graded of the Joule algebra. The grade and the Joule should be switched the order, right? Or
graded of the Joule algebra.
Or you take the Joule algebra of the graded vertex algebra.
Yes.
Okay.
So yeah. So if you have, so recall, sort of this is like sort of morally the physics definition of affine vertex algebra. So sort of like strings inside this Poisson space G star, which is a finite dimensional algebra. And so how do you actually make this concrete mathematically? Well, it's justified in many ways. So the associated gradient of this vertex algebra with respect to the Lie filtration is just jets inside the space. Another way to formalize it is that there's this notion of Joule algebra, which is an algebra attached to any vertex algebra. And the Joule algebra of this associated gradient is just functions on this space. And there's a quantization. If you forget the associated gradient, then the Joule algebra of this vertex algebra, the whole thing, is U of G. And the natural question is
there's also another gradation on this affine vertex algebra VKG by the conformal weights, and which induce the filtration on the Joule algebra as a filtered algebra, which make it almost commutative. So the associated graded algebra is also the function algebra on the G star. That's why I was saying that you switch the order of the Joule, then take the associated graded.
Ah, I see. Yes, I see what you mean. Yes.
And that automatically gives the Poisson structure as well.
Yes. Thank you. And yeah, so so a natural question is like, okay, so you can get universal enveloping algebras from these affine vertex algebras. Can you get quantum vertex algebras? So these very interesting deformations of universal enveloping algebras the same way. And so the idea is that they should arise as Joule algebras of these so-called Q-deformed, like Joyce's definition of Q-deformed vertex algebras. So again, I won't be able to say what these are, but they are essentially vertex algebras where instead of having poles of z equals w, you have sort of poles of z equals qw, z equals q squared w, and so on. And so like the advantage to this definition over other definitions of like similar like Q vertex algebras are well, so firstly, you can define Joule algebras of these things very easily. And secondly, it immediately comes with a sort of like whole host of examples, like coming from moduli stacks. Okay, so to actually solve this problem, one might try to use free field realizations. So what is a free field realization? So the basic example is comes from Bayes and Bernstein. So differential operators on P1 restricting to differential operators on A1 induces this map from the universal enveloping algebra of SL2 to the Weil algebra. So polynomials in X and the algebra generated by X and ddx, differentiation with respect to X. And it sends EHF, the canonical the usual basis of SL2 to partial minus X partial and X squared partial. Okay, so a free field realization, yeah, expresses one algebra or vertex algebra in terms of a simpler one. Okay. Now in the 90s, there was a lot of work on free field realizations, and even like indeed now. But in the 90s, there was a particular free field realization which will probably be useful to this. So Frankel, J, and Wang, for any ADE Lie algebra G, defined the free field realization of the affine vertex algebra at level 1. Okay, so there's a surjective map to the lattice vertex algebra attached to the co-character lattice, and it identifies this thing both as a representation of U of G hat and as a vertex algebra with the simple quotient of V1G, this firm module. And so taking G algebras gives you the map from U of G to the G algebra. So if you want to Q-deform this picture, how do you do it? Well, the obvious thing to do is that you should first take this V of lambda. Notice that this is just homology of a certain moduli stack. And then essentially, if you take these Qs and then you sort of, if you take the theta in the definition of these vertex algebra, so the things you Borcher's twist by, and you sort of like formally insert Qs into the theta, then you give this thing the structure of a Q-deformed vertex algebra. Now, Frankel, Jing, and Wang, again in the 90s, they defined a Q-deformed version of their free field realization. So a map from, this is now the Ver module attached to UQ of G hat. There's a map from that into this Q-deformed vertex algebra, which is the same thing as this like Q-deformed, there's a moduli space definition of this thing. And okay, so in their point of view, this thing is just a map of UQ of G hat modules. So they work with these things called like Q vertex operators, and they don't really have a notion of like Q-deformed vertex algebra. So the thing I'm trying to do at the moment, I'm working on at the moment is to get a map from UQ of G to the G algebra of this Q-deformed vertex algebra. And so one obvious question is like whether this thing is a Q-deformed vertex algebra, and if so, can you get a map into the G algebra of this thing? Okay. Like, there's been partial progress on this. For instance, like you can interpret a lot of this data geometrically in terms of objects on the moduli stack. Okay, so I think I should probably end here. So yes, thank you very much for listening, and thanks for coming.
Can you go to the previous page? I do have a few questions. Yes. On this. So for you have the quantum deformation of this vertex algebra, V1QG.
Yeah.
And so you also have the conformal structure with a conformal gradation, right? So does the dual algebra also have a filtration in a certain sense? Did you consider that? And
yes,
this
I believe
the almost commutativity condition as one construct this Poisson structure from filtered algebra for almost commutative version. But this time, almost commutativity probably should be
I believe
using
almost
the Q commutator. Am I correct?
So I understand the first question about whether the Lie algebra of this thing has a conformal grading. And so I think the answer to that is yes, because, or almost certainly yes, because so the definition of Lie algebra of a
you need that gradation in order to define the dual algebra.
But I believe this definition of Q-deformed vertex algebra actually plays well with respect to the grading. Grading.
So that also will suggest that there is a kind of a Q-deformed Poisson algebra structure on the associated graded part, which is not quite commutative. But when you specialize Q to 1, that will become a commutative, honest Poisson algebra. So I wasn't sure what the Lie algebra structure, the Poisson structure, will look like.
Is there a sort of
there is a standard construction if you have a filtered associative algebra. If the commutator goes to 1 degree below, so that's this algebra is in Ginsburg's and Chris's book called almost commutative algebra. So there is associated graded algebra which is automatically the filtered. It's automatically Poisson algebra. And all of this coming from a vertex operator algebra very nicely. One is the associative multiplication in Drew algebra, or it's coming from the nodes at -1, and the D bracket is coming from the node at 0. I didn't find this part in your paper, so I felt to ask you.
No, yeah. So this part is not part of the paper. So
Okay.
But okay. So I don't. So the question. So if you take associated graded of this thing, I think you could probably write down. You could probably write down axioms that this thing has to satisfy this like Q-deformed Poisson vertex algebra structure. But then the question is whether this would be the same as the notion of Q-deformed Poisson vertex algebra you're thinking about.
Yeah.
And to that question, I don't actually know the answer, and I think it's a reasonable one.
And my another question is going back to the quantum vertex algebra and Q-deformed. And He-Sheng Li has quite a series of papers on quantum vertex algebras. So they have, and they also have a paper talking about the vertex coalgebras, but that coalgebra doesn't seem to be the same as what you are talking. That
so I think
it's in the category of vertex algebras where the tensor product is just the honest vector space tensor product without any thing as you have with this field Z.
Yes, so I think there are a bunch of different notions of quantum vertex algebra floating around, and I essentially am very confused about how they're related, because I think partially it's
I guess here you call quantum because of the existence of this R matrix.
Yes.
The Z.
Yes.
And I believe He-Sheng Li's quantum was vertex algebra was following Karsten and Eddinghoff's.
Yeah. So I was under the impression most other notions of like quantum vertex algebra is more similar to this like Q-deformed vertex algebra definition.
Yeah, this one I like it. It seems to be just reflecting what the vertex algebra structure, especially for this R matrix appearance here.
Yeah. So I think like so the main question to like about whether like one should actually like this definition is sort of, can you define some sort of like like whether this category of representations is so ideally you want it to be something like a factorization category or something.
That's right. Could you actually on this question, what do you have in mind with the factorization E2 category?
I don't know. I think
Stella and Luria, they know better. So if Zhongzhu, you want to have
well, the E2 categories are the factorization. So in what sense?
Yes, I put this.
There is a notion of factorization algebra, which is sort of very naive, but it's working. So basically, you have kind of, if you have, it's an assignment of algebra in the simplest case to an open subset of your topological space. And if they disjoint, you have tensor product. So this kind of things. Yeah,
I know you take the divisors or the diagonals.
No, It's pure topological. It's not no divisors. It doesn't have to be. It's topological. It's you can do it. You can say what is a factorization algebra without algebraic geometry. Yeah, there is a book of Kevin Costello.
So I try to think the factorization here, because in the quantum case, in the classical, just look at all the diagonals, but for the quantum, whether I should have the curved diagonals.
Listen, it's all about the same story. For example, Alyosha started, he explained what is a vertex algebra using this string theory. Of course, it's not necessary, because you can work with quantum field theory, yeah. So then it's basically just axiomatization of the operator product expansion, or rather of its chiral part, because in general you should have a complex conjugate part as well. But it's just a holomorphic part or meromorphic, doesn't matter, without complex conjugation on the curve. Yeah, you place a vertex operator in the point, and you should think of this curve where all that happens as a space-time. Yeah, and so then this operator product expansion of these operator fields is axiomatized in the structure of vertex operator algebra. You can do it in any dimension. So E2 categories, it's just, or E2 algebras, it's just another way to axiomatize what is an operator product expansion in quantum field theory, roughly speaking.
I think I might have meant, I think I meant this remark in a slightly different way. I completely agree with what you said, but say you forgot the R matrix, and let's say this was just commutative for R equals 1, then this is some sort of like quantum vertex bialgebra, let's say, well, like vertex bialgebra. Then, so okay, if it was just a bialgebra, then it would then its category representations would be an E1 category, so just a monoidal category. But then in this case, you don't really have a monoidal structure. What you do have is that if you have any modules A and B, then you have a map from A tensor B to A tensor B bracket bracket Z. And okay, and you can write down a bunch of sort of compatibilities between this thing. And all I'm saying with this question, with this sort of thing in question marks, is that unless you can sort of formalize this as some sort of like structure living over the Rn space, I feel like it would be very hard to tell whether this definition is sort of correct or not. Right, but yeah, thank you very much for the questions.
Zongzhu probably refers to the work which goes back to 90s, like Frank Rishitihin and other stuff. I wrote something on meromorphic tensor category.
Yeah, I read that paper.
Yeah. There's many other people. Yeah, all right, but but you should do something with it. Then you will see whether this is the right definition or not.
Yes.
So that's the main point. But Alyosha, I have a different question. I'm looking through your slides, and you have some answer. And actually, I looked at your paper. You have some answer for CoHA of a curve, which I believe it's a category of coherent sheaves on the curve. Yeah. And somehow it looks like you do have some description, but it's kind of, it's not very explicit.
Yeah, so the problem I'm having is, so this expresses the cohomology of a curve in terms of 3 simpler cohomologies. So rank 0, 0 cohomology is very easy. This is just a symmetric algebra. Yeah. Rank 0, 1 is sort of semi-easy. So there's a stratification on this space, such that on each sort of stratified
so
piece.
What is rank? So what are the notations? So rank and degree or what?
So this is just rank. This is rank.
Just rank.
Yeah.
And
so like.
Okay.
Yeah. So this is, none of these spaces are connected. So these are disconnected, labeled by degrees.
All right, but no, I'm confused. No, I'm totally confused. What about vector bundles? Are these parts of your?
No, so there's a stratification on these spaces, and then like the open piece is vector bundle.
I see. So it's just a rank, and you don't care about degree, which is a little bit strange, because when you fix rank, say rank equal 2, say on P1, then you have infinitely many, too many, I would say, coherent sheaves with this rank, like even vector bundles of n plus of minus n, how to multiply.
Oh yeah, so these formulas do definitely include the degree.
I see. So okay, you see the reason why I'm asking you because probably you know there is this work of Schiffman and Vassero, which they will probably never publish, but I saw the formulas. You can email to Olivier, and they're very nice. They do have explicit shuffle type answers, which it should be for CoHA of well, smooth projective curve. And certainly the answer looks in such a way that when I kind of saw your paper first, the title, I was sure that those formulas are inside, because it looks as a quantum vertex algebra. This type of, I mean, they're written in terms of generating functions, yeah, and therefore, yeah. Okay, this is kind of one remark. Another is a question, because when you work with Borel-Moore, I mean, it's kind of probably inspired by this Ben Davison story. When you have a universal enveloping algebra, yeah, it admits a filtration, and associated gradient is commutative.
Yes.
So same story for CoHA, which is a sort of a quantum enveloping algebra, and this is what we actually wrote with Maxim in that old paper. But Ben somehow made it precise, so there is a weight filtration, and such that the associated graded is sort of a symmetric algebra of this BPS Lie algebra. You know, like CoHA is sort of it's kind of the size of enveloping algebra, but there is a Lie algebra, and this is what Ben constructed, I think, with Mainhardt. All right,
yeah,
so my question is what this weight filtration is for CoHA on the curve. Because I remember we made some computation with Roma Fedorov and my son, kind of 1 minute computation of CoHA of the curve, and we arrived to the commutative part based on the old work of Heinlot, which you probably also saw. All right, so you can easily see this associated graded, this symmetric algebra of cohomology, essentially, of your curve, maybe shifted. But this weight filtration, it's somehow puzzling. This is what makes the whole story non-commutative. So my question is, what is this weight filtration, which Ben likes so much in the case of CoHA of the curve?
So I think I think the answer to this is I don't know. So I. Okay, yes, I honestly had not actually thought about connecting this with the weight filtration.
Yeah, okay, so let's then leave it the question.
Yeah.
Yeah.
I mean, it might have to do with the fact that no, I don't know.
Yeah, okay. All right. But actually, Ben is not very far from Oxford, so at least it's the same time zone. You can
Yes.
you can ask him. Yeah, of course. And then another question, I believe that sort of bigger, but it's doable after you have this abelian localization things is CoHAs for in higher dimension. What you mentioned, it's you mentioned this free field approach, yeah, and this free field story, it geometrically it appears when you do torus localization. For example, you know, there is this three-dimensional partitions. This is generating function given by McMahon formula, but you can interpret, you can derive this formula using the free field approach. Basically, you consider slicing, you consider a family of parallel planes, say choose one of the coordinate planes and take just parallel planes, slicing your three-dimensional partition. So at each slice, you see an ordinary two-dimensional partition. So you have the Fock space, like if you like Nakajima-Grainovsky, yeah, and you have the corresponding vertex separator presentation for this particular plane.
And so what's the reference to this?
Excuse me?
What's the reference for this? I'm not aware of the story.
I think it goes back to the initial paper by Nekrasov, Akunkov, and maybe even Waffa. It was maybe it was half physics at the time. It's yeah, it was before this MNOP, Malik, Nekrasov, Akunkov, and Pandaripande's story about Donaldson-Thomas invariants. It's a preceding, it's kind of historically, I think it was the first paper. Anyway, one on the team was Akunkov, and probably it was a paper, but maybe not Nekrasov, maybe Rishetikhin. I can find the reference and send it to you. But anyway, or you can try to do it yourself because it's kind of very intuitive story. You have three-dimensional partitions and you consider kind of imagine that octant and like sticking out z-axis, x and y horizontally, and you move from infinity on y-axis through the origin and then all the way to the infinity on x-axis. Sort of, yeah, all right. And this will be the direction of the product of your vertex separators. Each vertex separator sits in the two-dimensional slice, acts in the Fock space spanned by two-dimensional partitions, which is same as the Hilbert scheme, of course, if you work equivariantly. And basically the generating functions, which gives you McMahon, it's a sort of a matrix element, principal matrix element of this product of vertex separators. And this is a free field approach to this partition function. And the same free field approach, which is more complicated, it works in particular in this W algebra story with instantons of higher ranks. It's more or less the same. So which means that if you have an abelian localization, you can compute many CoHAs and many VOAs, just considering natural representations of CoHA in the basis of fixed points. Because it's a general kind of a rule is that you have your CoHA of whatever is it, of your category, then you have a category of stable framed modules over this CoHA, whatever this means. I think I wrote a paper on that in 2014, but anyway. And so your CoHA acts, CoHA of the stack of objects of your category acts on the cohomology of the stack of framed objects. And so then the CoHA of a three-dimensional complex vector space, which is equivalent one vertex, three loops, and the cubic potential, it can be easily computed. And it's somehow related to this three-dimensional partition story. And so then you consider representations in some moduli space of framed sheaves, look for fixed points there, and you see some free field realization. So you can get a lot of formulas, which probably physicists will be happy to see. Yeah, so I'm a bit, but for P1, for example, if your curve is P1, you have a torus C star action on P1, so probably you can compute.
You mean just for curves?
Yeah, just here, write very explicit formulas.
Yes. Oh, I see. Wait, you mean you apply abelian localization again to get?
Yeah, not including the curve itself. Yes.
Yeah. Okay, so you work with like P1 mod T. Okay. That is, yeah, but there's also I'm not sure if you know there's an equivariant version of so it's slightly more trivial to do, but like if you have a torus action on the moduli stack, then or no, a group action on the moduli stack, then you can also get a vertex algebra structure.
Yeah,
so,
but you see this, I mean, this Dominic made a nice observation, but it's really deficient because it's essentially lattice algebras. You take like sort of homology of your stack and use it as a lattice. I mean, it's, of course, you have this additional theta symmetrization, but you should really somehow understand this perverse sheaf of vanishing cycles. And of course, Dominic knows this very well in the shifted symplectic framework, not just for three-color BR, probably it's more general.
Right.
Of course, otherwise kind of it limits your applications. And another also kind of good idea is since you mentioned that your D-branes are even dimensional, which means that you prefer coherent sheaves. But here in the room, there are people who like Floer theory, who like Fukaya categories, and it's as good as a derived category of coherent sheaves. So CoHAs for Fukaya categories, it's another open question. You see, the problem with CoHA, and actually, is that we did not really prove that it's derived invariant, which means that if you compute.
What do you mean by derived invariant?
Well, actually, definition of CoHAs somehow, if you have a category, you see, if your category, maybe it's in your, it's part of your formalism because you work with stack of objects, and so for derived equivalent categories, it's equivalent stuff. But at the time long ago, when we wanted categories rather than stacks, there was a CoHA was defined for a particular T structure of a derived category. If you change the T structure, the CoHA is different.
I see.
When you define it using extensions, blah, 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 it's not clear whether you get the same answer. So then I don't know whether your formalism helps to prove or to show that CoHA can be derived, can be defined in the
derived categories.
Derived, yeah.
Well, I think so. Yeah. So this is, I mean, so the answer is not that I know yet, but I think there's this answer floating around that there should be some relation between. I wrote it down a bit more explicitly above. There should be some. Where is that? Yeah, so there should be some relation between passing between the abelian category and the derived category and doubling.
Yeah, but doubling is, doubling.
Like, so you haven't, this inclusion gives you a map of vertex algebras.
Yeah. I understand. I understand the point, but this doubling, I would rather like to have CoHA of the derived category than double of the CoHA of one half of it. You see, it's a deficiency of even the original of the constructible whole algebras, as you know, because it gives only one half of the quantum group, and you should add the other half by some unnatural things, like considering, for example, two periodic complexes like Bridgeland likes, but it's sort of artificial.
Yes, I think, the main point I'm making with this is that this is simultaneously something which is fairly natural and also might have to do with doubling, that might,
Yeah. Okay, if you actually, even this will be very interesting achievement for me, that if you can indeed define CoHA for dB of A, and prove that it is double.
Oh no, I don't think I'm making such statements.
But it would be nice. I mean, it's
I agree.
natural, and it would be really nice. Then, of course, I mean, it would be nice. Okay, more questions?
Right.
Well,
thanks very much for the questions.
Well, if there are no more questions, well, thank you again for very interesting talk. And now people can read your